In the last video I showed you how this equation here changes the dynamics of a system and allows us to stabilize it at 0. Let's now go further than control theory and look at an actual example to see this control technique in action. We look at the equations, code of the implementation, and simulation results. We are using this system here. We have two masses that are connected with a couple of springs and some damping elements to a fixed reference. A force pulls on the bottom mass, and this is our output from the controller. If we pull at the bottom mass, both masses will start to move. They are connected after all, and if we let go, they go back to the origin. Because of the values chosen for damping, one of them oscillates while the other more or less crawls back to the origin. I chose this system because we can study a couple of different concepts. Stabilizing the system around a random point that is not the origin. Later on we can use the same system to cover pole placement, the influence of parameter uncertainty, and how to implement an integrating component into the control concept. If you want to follow along with the implementation, here are the dynamical equations of motion for the system and the parameters. I will give you a few seconds to pause the video and screenshot them, so you have them for reference in case you need them later on. In the last video I showed you the controller looking like this here, where our control input U is equal to minus controller gains K times the state of the system. This equation is not wrong, but if we want to stabilize a point that is not equal to 0, we have to make a few changes. First, instead of using the state x, we use x tilde. This is the error between our state and the reference point. The reference is the actual goal point. So let's just put that in. We need one more thing, that is U reference. In our system, this is the constant force needed to hold the system in the goal point. Depending what kind of system you have, you might not need it, but this is the full equation. If you have never seen how to create a simulation from scratch, just stick around till the end. I have a few video recommendations for you. The core of our simulation is the function describing the dynamical movement, which also contains the implementation of the controller. We create a function with the following inputs: simulation time and state as required by our integrator, then the parameters of the system, afterwards controller gains, our target point, and finally our U reference input force. Inside our function we calculate the dynamical movement, and we return that together with our controller force at the end, as you can see here. The controller force is optional and only used for plotting in the end. For the code, here at the start we have to do a few things, optional, but I would highly recommend them. First, you should always start with a short doc string for documentation. Just a brief outline what the function does and what the inputs and outputs are. Makes reusing it in 6 months a lot easier. More important for long and complicated functions, but a good habit to have. Second, you should subscribe to the channel and like the video. This way you won't miss future videos and it really helps grow the channel. Also a very good habit to have. That aside, after we are done with both steps, we continue the code, split the state up into individual variables. This is more convenient to work with when implementing our equations of motion, as you will see in just a second. Then the most important part of the video, the controller. Here we implement the equations I showed you before. Our input, so the force of the system, is equal to minus the controller gains K times the difference between the actual system state from the simulation and the goal point, so x tilde, plus the reference force U. I always pass in the goal point and the reference force as an anonymous function from the outside, and with this implementation we just grab the correct value at the current simulation time. Then we continue to the last step and implement our dynamical equations of motion. Put everything into a return vector and we are done with this part. We can now call this function with our ODE45 integrator and check out the result of the simulation. We are looking at 3 different results. We always initialize our system at the location x2 equal to 0.5. In the first simulation, we just let the system go and stabilize it at 0 with the controller. In the second simulation, we let the system go, provide x equal to 1 as goal point, and we use the correct U reference. And in the final simulation, we again let the system go, provide the same goal point, but this time do not use U reference. As you can see, our system also stops, but not at the desired end location, but somewhere in between. This is the same effect as the one in the PID controller video if we only use the P controller, if you remember. It is explained right about here in the video. So let's look at some plots, only at the positions of the 2 masses. The top plot plots the position of the top mass and the bottom plot the bottom mass. First simulation, second and third. The third one is not too interesting, since we do not use U reference, so we do not hit our desired endpoint. This could be fixed by implementing an integrator via state expansion. If you are interested how to do this, please let me know in the comments. But this is not the interesting result in the plot, something else is. If we take the simulation results of the second plot, move it down by the constant offset of the goal point, and mirror it around the x-axis, we see that the dynamical responses are identical. We stabilize the different point, but the dynamics of the responses are identical. And what this means is the following. We can analyze how a system behaves around 0, and we know that it will behave the same when stabilizing a point that is not 0. Whenever we are analyzing what different pole locations mean in the following videos, we are analyzing how errors decay down to the origin. It is just more convenient to do that. And as you saw here, with a comparable error at the start, all errors decay the same. At least the dynamics are the same. A few minutes ago, I promised to give you some video recommendations on creating simulations. I have made a couple of videos myself that really go in depth. From the system equations to the framework over to plotting, all in one video. And I did that for 3 different examples. I will put the links in the video descriptions. I'm planning to make new thumbnails for those videos eventually for consistency, so best use the links in the video description to find them. Thank you very much for watching. Like, comment, share and subscribe. Bye for now.